Variance and standard deviation are properties of a probability distribution that are related to the uncertainty. Since uncertainty is such an important concept in quantum mechanics, we need to know how to quantify how uncertainty results from probability distributions. So let's talk about the variance and the standard deviation. These questions are related to the shape of a probability distribution. So if I have a set of coordinates, let's say this is the x-axis, and I'm going to be plotting then the probability density function as a function of x. Probability distributions come in lots of shapes and sizes. You can have probability distributions that look like this, probability distributions that look like this. You can even have probability distributions that look like this, or probability distributions that look like this. And these are all different. The narrow peak here versus the broad distribution here. The distribution with multiple peaks, or multiple modes, in this case it has two modes, so we call this distribution bimodal, or multimodal. And then this distribution, which is asymmetric, has a long tail in the positive direction and a short tail in the negative direction. We would say this distribution is skewed. So distributions have lots of different shapes, and if what we're interested in is the uncertainty, you can think about that roughly as the width of the distribution. For instance, if I'm drawing random numbers from the orange distribution, the narrow one here, they'll come over roughly this range. Whereas if I'm drawing from the blue distribution, they'll come over roughly this range. So if this were, say, the probability density for position, say this is the squared magnitude of the wave function for a particle, I know where the particle represented by the orange distribution is much more accurately than the particle represented by the blue distribution. So this concept of width of a distribution and the uncertainty in the position, for instance, are closely related. The broadness is related to the uncertainty. This is fundamental to quantum mechanics, so how do we quantify it? In statistics, the broadness of a distribution is called the variance. Variance is a way of measuring the broadness of a distribution, for example. So suppose this is my distribution. The mean of my distribution is going to fall roughly in the middle here. Let's say that's the expected value of x, if this is the x-axis. Now, if I draw a random number from this distribution, I won't always get the expected value. Suppose I get a value here. If I'm interested in the typical deviation of this value from the mean, that will tell me something about how broad this distribution is. So let's define this displacement here to be delta x. Delta x is going to be equal to x minus the expected value of x. And first of all, you might think, well, if I'm looking for the typical values of delta x, let's just try the expected value of delta x. Well, what is that? Unfortunately, the expected value of x doesn't really work for this purpose because delta x is positive if you're on this side of the mean and negative if you're on this side of the mean. So the expected value of delta x is 0. Sometimes it's positive, sometimes it's negative, and they end up canceling out. Now, if you're interested in only positive numbers, the next guess you might come up with is let's use not delta x, but let's use the absolute value of delta x. What is that? Well, absolute values are difficult to work with since you have to keep track of whether a number is positive or negative and keep flipping signs if it's negative. So this turns out to just be kind of painful. What statisticians and physicists do in the end then is, instead of taking the absolute value of a number to make it positive, we square it. So you calculate the expected value of the squared deviation, sort of the mean squared deviation. This has a name in statistics. It's written as sigma squared, and it's called the variance. To do an example, let's do a discrete example. Suppose I have two probability distributions, all with equally likely outcomes. Say the outcomes of one distribution are 1, 2, and 3, while the outcomes for the second distribution are 0, 2, and 4. Put it graphically, these numbers are more closely spaced than these numbers. So I would expect the broadness of this distribution to be larger than the broadness of this distribution. You can calculate this out by calculating the mean squared deviation. So first of all, we need to know the mean. The expected value of x is 2 in this case, and also in this case. Knowing the expected value of x, you can calculate the deviations. So let's say delta x here is going to be -1, 0, and 1 are the possible deviations from the mean for this probability distribution, whereas in this case it's -2, 0, and 2. Then we can calculate the delta x squareds that are possible, and you get 1, 0, and 1 for this distribution, and 4, 0, and 4 for this distribution. Now when you calculate the mean of these squared deviations, in this case the expected value of the squared deviation is 2/3, whereas in this case the expected value of the squared deviation is 8/3. So indeed we did get a larger number for the variance in this distribution. So you can think of that as the definition. This is not the easiest way of calculating the variance, though. It's actually much easier to calculate the variance as an expected value of a squared quantity and minus the square of the expected value of the quantity itself. So the mean of the square minus the square of the mean, if that helps you to remember it. You can see how this results fairly easily by plugging through some basic algebra. So given our definition, the expected value of delta x squared, we're calculating an expected value. So suppose we have a continuous distribution now. The continuous distribution expected value has an integral in it, so we're going to have the integral of delta x squared times rho of x dx. Now delta x squared, we know what delta x is. Delta x is x minus the expected value of x, so we can plug that in here, and we're going to get the integral of x minus expected value of x squared times rho of x dx. I can expand this out, and I'll get integral of x squared minus 2x expected value of x plus expected value of x quantity squared rho of x dx. And now I'm going to split this integral up into 3 separate pieces. First piece, integral of x squared rho of x dx. Second piece, integral of 2x expected value of x rho of x dx. And the third piece, integral of expected value of x squared rho of x dx. Now this integral you recognize right away. This is the expected value of x squared. This integral, I can pull this out front since this is a constant. This is just a number. This is the expected value. So this integral is going to become 2, I can pull the 2 out of course as well, 2 times the expected value of x, and then what's left is the integral of x rho of x dx, which is just the expected value of x. This integral, again this is a constant, so I can pull it out front, and when I do that I end up with just the integral of rho of x dx. And we know the integral of rho of x dx over the entire domain. I should specify that this is the integral from minus infinity to infinity now. All of these are integrals from minus infinity to infinity. The integral of minus infinity to infinity of rho of x dx is 1. So this, after I pull the expected value of x quantity squared out, is just going to be the expected value of x quantity squared. So this is expected value of x squared. This is, well, I can simplify this as well. This is the expected value of x quantity squared as well. So I'm going to erase that and say squared there. So I have this minus twice this plus this. And in the end, that gives you expected value of x squared minus the expected value of x squared. So, mean of the square minus the square of the mean. To check your understanding of how to use this formula, I'd like you to complete the following table. Now, I'll give you a head start on this. If your probability distribution is given by 1, 2, 4, 5, and 8, all equally likely, you can calculate the mean. Now, once you know the mean, you can calculate the deviations, x minus the mean, which I'd like you to fill in here. Then square that quantity and fill it in here, and take the mean of that squared deviation. Same as what we did when we talked about the variance as the mean squared deviation. Then, taking the other approach, I'd like you to calculate the squares of all of the x's and calculate the mean square. You know the mean, you know the mean square. You can calculate this quantity, mean of the square minus the square of the mean, and you should get something that equals the mean squared deviation. That's about it for variance, but just to say a little bit more about this, variance is not the end of the story. It turns out there's more. I mentioned the distributions that we were talking about earlier on the first slide here. Keep forgetting to turn my ruler off. The distributions that look like this versus distributions that look like this. This is a question of symmetry, and the mathematical name for this is skew, or skewness. There's also distributions that look like this versus distributions that look like this. And this is mathematically, this is called kurtosis, which kind of sounds like a disease or perhaps a villain from a comic book. Kurtosis has to do with the relative weights of things near the peak versus things in the tails. Now, mathematically speaking, you know the variance, let me go back a little further. You know the mean, that was related to the integral of x, rho of x, dx. We also just learned about the variance, which was related to the integral of x squared, rho of x, dx. It turns out the skewness is related to the integral of x cubed, rho of x, dx, and the kurtosis is related to the integral of x to the fourth, rho of x, dx. At least those are common ways of measuring skewness and kurtosis. These are not exact formulas for skewness and kurtosis, nor is this an exact formula for the variance, of course, so I'm taking some liberties with the math. But you can imagine, well, what happens if you take the integral of x to the fifth, rho of x dx? You could keep going, and you would keep getting properties of the probability distribution that are relevant to its shape. Now, you won't hear very much about skewness and kurtosis in physics, but I thought you should know that this field does sort of continue on. For the purposes of quantum mechanics, what you need to know is that variance is related to the uncertainty, and we will be doing lots of calculations of variance on the basis of probability distributions derived from wave functions in this class.